Introduction to Physical Science, Chapter 4.1 Physical Characteristics of Matter. In the beginning, God created the heaven and the earth. Genesis 1:1. Can you imagine what it must have been like before the creation of matter? Scientists use the term matter to refer to all the substances in God's creation. Material things are made up of matter. They are physical things that you can touch, taste, feel, see, or smell. Even the invisible air around you is a material substance. You can feel air moving. The universe as a whole includes everything God created. The physical universe, however, is only the material part of reality. God is a spirit, it says in John 4:24. Although he is a part of the universe as a whole, he is not part of the physical universe. He is immaterial, which means he does not consist of matter. As you may remember, your soul and spirit are also immaterial parts of the universe. Some people say that nothing can be real unless it is physical or material. This is the basic belief of the philosophy of materialism. It is not logically possible, however, for anyone to truly deny the reality of immaterial things. For example, your brain is material. It is made of substances that can be perceived by the senses. Your mind, however, is immaterial. It cannot be seen or felt. Yet you know it is real because you have the ability to think and reason. Even though scientists can observe only the material parts of the universe, they cannot deny the reality of their own immaterial minds. Most important, they cannot truly deny the existence of the immaterial creator of the things they study. 3 states of matter. Every physical thing that has mass and takes up space, whether large or small, alive or dead, visible or invisible, consists of matter in one of its 3 forms or states: gas, liquid, or solid. The air you breathe is matter in the state of a gas. The water you drink is matter in the state of a liquid, and the salt on your table is matter in the state of a solid. Staying in shape. Of the 3 states of matter, a solid is the only one that has a definite shape and a definite volume. Volume is defined as the amount of space a substance occupies. Grasp something solid like a pencil and try to squeeze it. Notice that the pencil is not easily compressed and that it retains its shape. Scientists have learned that matter is made of innumerable invisible particles called atoms. In a solid, these microscopic, too tiny to be seen without a microscope particles are very close together and vibrate in fixed positions. Thus, the macroscopic, or large enough to be seen with the unaided eye, object retains a definite shape. Running into corners. A liquid has definite volume, but it has no definite shape. It will change to the shape of the container you put it in. The microscopic particles of matter in a liquid are usually not as close together as those in a solid. Therefore, the particles can move about more freely. Note that when you pour water from a glass, some water adheres to the glass. The water particles along the side of the glass move very little, while the water particles in the middle of the glass flow out past them. The same behavior is true of all other liquids. Also, some liquids flow more easily than others. For example, water flows much more easily than corn syrup. Filler up. A gas has no definite volume or shape. Because of this flexibility, a gas will completely fill any container into which it is placed. Another property of a gas is that gas particles can easily be pushed together, compressed. The most familiar example of a gas is air. Although air is invisible to us, it is actually made up of many microscopic particles of matter. You can demonstrate the properties of a gas by pumping air into a bicycle tire. As you inflate the tire, the bicycle pump forces more air particles into the tire tube. The fact that the pump is able to force more air into the tube demonstrates that the particles in a gas are far apart. When more air particles are added to the tire tube, the particles of air that are already inside the tube are pushed closer together. Solid to gas, a direct flight. In the environment, a substance exists naturally as a solid, a liquid, or a gas. The state of a substance at any particular time often varies as the physical conditions of temperature and pressure change. In the laboratory, however, where a scientist can control temperature and pressure, a substance can be forced to remain in a particular state. In our environment, carbon dioxide normally exists as a gas, which is used by plants in the process of photosynthesis, but under controlled conditions. Carbon dioxide can be frozen into a cold white solid by cooling the gas under pressurized conditions. The solid is called dry ice because it does not melt into a liquid form under normal temperature and pressure conditions, but rather changes directly from a solid back to its natural form, a gas. Scientific explorer, molecular masquerade. Water is a fascinating substance because it can exist naturally in all three states. The change from one state of matter to another involves a physical change. Although physical properties are altered when a substance undergoes a physical change, its chemical composition remains the same. To observe the physical changes of water, first fill an ice cube tray with water and place it along with a metal spoon into a freezer until the water becomes ice. Now, take some ice cubes and drop them into an empty beaker or tea kettle. Using a hot plate, heat the ice until it melts. When ice is heated, the molecules begin to vibrate faster and faster until the attraction between them is no longer strong enough to hold them in their fixed positions. As the molecules begin to move about, the ice becomes a liquid. The molecules are still attracted to each other, but they can move enough to allow the liquid to take the shape of its container. The molecular attraction does not hold them in a rigid structure as it did in ice. Continue to heat the water until it boils. As you increase the heat, the attraction between the molecules will eventually have no effect as they move farther apart out of each other's reach. At that point, the molecules move freely from place to place, and the liquid water becomes a gas. To observe the gas returning to a liquid state, take the spoon out of the freezer and hold it over the steaming beaker. What happens to the spoon? Water droplets collect on the spoon as the steam condenses or changes back into water. Regardless of the state, ice, liquid, or steam, you still have water. Physical properties. God's precise order is displayed throughout creation. Each substance has unique properties that set it apart from all other substances. Physical properties are those properties of a substance that can be determined without changing it into a different substance. These properties distinguish one kind of matter from another. For example, water has freezing and boiling points, which are completely different from those of oil, sand, steel, or any other material. The temperatures at which a substance changes its state are unique characteristics of that substance. Other physical properties of matter include odor, color, hardness, density, ability to be dissolved, and electrical conductivity. Points of opposition. Don't you like to drink hot chocolate on a cold day? We classify things as being generally hot or cold. However, what feels hot or cold to one person may not feel the same to another. To determine precisely how hot or cold something is, scientists use readings of temperature as an objective numerical way to measure hotness or coldness. Quantification is the systematic process of accurately measuring the things of nature and their parts. The numerical measurements obtained through quantification are always reported with their appropriate units, such as degrees for temperature or centimeters for length. The freezing point of a substance is the temperature at which a liquid changes into a solid. The temperature at which a liquid changes to a gas is called the boiling point. Scientists quantitatively describe the freezing and boiling points of liquids using a thermometer to measure temperature. As you know, a thermometer is divided into units called degrees. The two most common temperature scales, the Fahrenheit and the Celsius scale, are both based upon the freezing and boiling points of water. If you were to place a double scale thermometer into a slushy mixture of crushed ice and tap water, the thermometer would have readings of 32 degrees Fahrenheit and 0 degrees Celsius. We say that these two readings are equivalent because they indicate the temperature at which water freezes or ice melts. Although the two temperature scales are numerically different, they both register the same condition in the water. A disappearing act. If you mix sugar with water, you will notice that the sugar seems to disappear in the water. It dissolves. Solubility, the ability to be dissolved, is a physical property because it does not alter the chemical composition of either the sugar or the water. The sugar really has not disappeared. There is still sugar in the water. If you wanted to see the sugar, you could boil away the water and the sugar would be left behind. One factor that affects solubility is temperature. If you keep adding sugar to the water, eventually some of the added sugar will not dissolve. By raising the water's temperature, more of the added sugar will dissolve. Some substances will not dissolve in water, no matter how much you raise the temperature. Particles of sand may resemble sugar, but they will not dissolve, even in boiling water. If you mix oil and water together, the oil floats on top. Oil and sand have the physical property of being insoluble, which means unable to be dissolved in water. A weighty matter. Every object has the physical property of mass. Mass is a measure of the quantity or amount of matter an object contains. Weight is the measure of the gravitational force or the downward pull of a planet on an object. Weight depends on mass. The more mass an object has, the greater the downward pull on it, and consequently, the more the object weighs. If, however, the object is weighed where the gravitational force is weaker, its weight will be even less, though its mass will not have changed. For example, if you were to weigh yourself on top of a mountain, your weight would be slightly less than if you weighed yourself near the beach at sea level. Your body would have the same mass, but the effect of gravity on your body would be slightly less on a mountain, and a sensitive scale would show this difference in the weight measurement. Definite density. Did you ever wonder why you usually have to shake a bottle of Italian salad dressing before using it? If you let the bottle stand for a while, you will notice that the liquid separates into distinct layers. This separation occurs because the vegetable oil in the salad dressing is insoluble in the vinegar. The reason the oil floats on top of the vinegar instead of the vinegar floating on top of the oil is that the oil is lighter than the vinegar. What you really are observing is the difference in density between the oil and the vinegar. Density is the mass of a substance divided by its volume. You will recall that volume is the space something occupies. Because every substance has its own particular density, this physical property may be used to help in the identification of an unknown substance. Because volume involves 3 dimensions, the volume of a substance is usually recorded in cubic centimeters, or cm3. Density is often measured in grams per cubic centimeter, which is grams divided by centimeters cubed. Since the milliliter, or ml, is equal to a cubic centimeter, density may also be recorded as grams per milliliter, or G divided by ml. Check it out, mass measures. The mass of a small object is commonly measured in grams, the standard unit of mass in a metric system. After choosing a small object of unknown mass, place the object on one pan of an equal arm balance. Next, select from a set of known weights a weight that feels similar in mass to the unknown mass and place the weight on the other side of the scale. If the side containing the known mass rests lower than the side with a substance of unknown mass, you will need to remove the weight and replace it with a smaller one. If the side with the unknown mass rests lower, you should place another weight on the balance next to the one you already added. Continue trying various combinations of the known weights until the scale is balanced, until the arm remains in a stable horizontal position. After you have balanced the scale, you can sum the values of the known weights sitting on the scale to find the mass of the substance. Instead of telling your friends that the object is heavy or light, you can give them a specific mass measurement recorded in grams. Density differences. Suppose we weighed 2 bricks of the same size, one made of iron and the other of clay. Since iron is denser than clay, the iron brick would be the heavier of the two. If we wanted the bricks to weigh the same amount, we would have to increase the volume of the clay brick or make it bigger until it could contain the same amount of matter as the iron brick. It is impossible for 2 objects with equal volumes but differing densities to weigh the same amount. Objects made of materials with different densities can either be of the same volume and different weights, or the same weight and different volumes. Generally, density increases as a substance changes from a gas to a liquid and from a liquid to a solid. In other words, a solid is more dense than a liquid, and a liquid is more dense than a gas. Water molecules, however, behave in an unusual way as they near their freezing point. Like other substances, water molecules draw closer together as the temperature drops, forming a heavier, denser mass of molecules. Water reaches its highest density at 4 degrees Celsius, but once the temperature of water drops below 4 degrees Celsius, something unusual happens. Instead of continuing to contract and become more densely packed, the water molecules suddenly begin to take up more space, resulting in a decrease in the overall density of the water. This decrease in density as water changes to a solid explains why ice floats in water instead of sinking. Ice molecules are arranged in rigid open structured formations which contain large amounts of empty space. The ice molecules must therefore remain farther apart from each other than the liquid water molecules, which intermingle freely. This amazing property of water clearly illustrates the provision of God for the creatures living underwater during the winter. Because the ice forming in the lakes and rivers floats on top of the water instead of sinking to the bottom, an ice layer is created which acts as an insulating blanket for the water below it. This blanket helps to prevent the water from freezing all the way to the bottom. In this way, God protects the fish and other living things in a lake or river from being frozen into a huge block of ice during the harsh winter months. Scientific explorer, sink or swim. To make your own density column, first pour 100 milliliters, or about a third of a cup, of light corn syrup into a 400 or 600 milliliter beaker or a tall drinking glass, being careful not to let the corn syrup touch the sides of the beaker or the glass. Place 100 milliliters of water into another beaker or a measuring cup and add 1 drop of food coloring. Then slowly pour the water into the beaker containing the corn syrup, allowing the water to trickle down the side of the beaker so that it will not disturb the bottom layer of corn syrup. Next, slowly pour 100 milliliters of vegetable oil down a different side of the container. Avoid mixing these 3 liquids. The dye from the water could blend into the corn syrup, confusing your results. You now have a column with different densities. Which liquid do you think is the most dense? To find out the densities of different objects, try dropping the following objects one at a time into your density column: a cork, a rubber stopper, a glass marble, a small plastic object, and a steel paper clip. An object will float in a liquid that is more dense than the object itself. Therefore, the denser objects will sink to the level of the denser liquids.